G'day guys, been doing another bit of experimentation on the GPZ 45 100 5000 series and just seeing how fast I can get these things clocking, as in how much dead time I can get away with before the system falls over. And I've looked at various ways of speeding it up and make things switch harder and faster so I can get that dead time down. The dead time's the off time between the transmit and receive, where the ground signals want to dissipate off, and you don't want to encroach on that die off there of the ground signals. You want it to be gone, then turn your receivers on, and well, actually, you do want to pick it up because it's using the ground balance circuit, but you don't want it amplifying the hell out of it and then swamping out your very, very small signals later on in the decay curves. So it's a bit of a balancing act. So at the moment, the standard delay, the way the detector works, that's taking all its electronics and switching into account. I can get it down to, I have got it down to 28 microseconds. It's really pushing it. It will have a hell of a lot of sensitivity, but it starts amplifying a lot of ground noise as well. And you could get some type of swamping on very reactive ground. It's probably not a good idea to do. But the other way of going too, if you open up the dead time, like this one here, I've got it tricked up so I can move the or the dead time. The terms are interchangeable. Dead time, off time. Dead means it's not receiving, basically. Well, it technically is still, but it's the space between the transmit and the actual target recovery signal that you want. You don't want ground noise signal. That wants to get cancelled out. It's gone, and just leave the target signals behind. But this, if you can see, oh dear me, I'll zoom in a bit if I can. Where am I? There. See those little arrows at the top there? That's in that off time, dead time between the actual receive. If you can see down there where it says 30.450 microseconds, that's that gap width. That is, it's a bit crunchy, this thing, but that's where those little arrows are sitting at the moment. There. Now, normally these detectors sit at about 35 or 36 microseconds, and by having it the way I've done it, I've gained 5 microseconds, having it come on 5 microseconds faster. But if we use a 0. I think I've got this. I'll give it full bore audio. If I got my little that thing 0.05 little spec there, and I hit the coil. It's in normal mode, by the way. Say if I hit the coil with it, right? It's very loud. And just say, for instance, that we wanted to use a greater off time, which I got this set up where I can do that. I've got some extra stuff in the electronics, so these will spread right out. Okay, I'm down to 0, and let's put my hand over here, make sure that, what am I on? Oh no, I'm going to do on that cursors or else it won't move. And I'll move this across onto the top there, and there. You can see the numbers now, 41.7. I can take it further than that, and it might be an idea to try doing it further than that. But I'll just do the same test. I'll just turn the volume back up on this. I use the that spec again, but you have a listen to that. The amplitude is way down in signal level. because we're not getting all the decay signal off this after it's been energized. So you want to use very, very small amounts of off time for tiny, tiny targets. And if you have big, reactive, noisy ground, and this is the other thing I was actually looking at with these detectors too. These, as they're specifically a gold detector as such. I'll get onto this in a second. But as they are specifically a gold detector, um, no, they're not really good around salt water, but you can make it work for detecting water lines on the beach and sandbars. Now, what I did then, I spread out those, well, the off time, dead time. Sometimes I interchange those two terms. It means the same thing. It's like saying dead and stop breathing, right? Same thing. Um, Off time, dead time. It just means the transmitter has finished transmitting and it waits a little bit before the receiver turns on to obtain signal recovery. It's just that massive amount of decay. You know, you got your flyback decay. You got the ground's been lit up like a Christmas tree. You know, it's a lot of energy coming back. It'll swamp your receiver, so you got to leave a delay there. And depending on what the ground is how big or how long that delay should be. Salt water should be a massive delay. Pipe clay should be a minimal delay. The local park, minimal delay within reason, depending on the ground makeup. It all to do with how reactive the ground is. Uh, you know, a lot of ironstone ground, uh, it doesn't have a really long decay. It does. It's much more than say normal soil, but it's not like salt water or anything like that. So it's all these variances you can have there, and that's why I always thought that it would be great if you had a detector and it came out and it had the variable off time. But maybe that's too complicated and people will get confused, and the manufacturers don't do that. I know there's a couple of them kicking around that do that, but you know, not the main players don't do it, as far as I know, unless they probably make specific underwater detectors. You could have it for that. You can have a variance there. But you know, this has got an off time at the moment of 41. I don't know how far you could switch that out. Maybe you know you could take it out to 50. I don't know. I'd have to actually test it and see how far. But I know you can go into about 28. It depends on the coil you're using as well. Like on this at the moment, I've got a double D coil and it's a bit of a slug. And you know, a very fast mono coil, you know, will help. Like at the moment, if I took this down to say um, 28 microseconds with that coil on it, the whole thing, everything in here will the transmitter is going to crash into the receiver, and all sorts of horrible things are going to happen, and the detector goes straight into coil over current. It just fails, and it is not conducive to doing that. But you know, we can go the other way. Maybe we can go a lot further. I've had these out to about 44, 45, 46. And they work fine. The other thing to make sure too, does the detector still ground balance when you do that? Are we getting so far away from where things are set up, you know, um, with that the magic mathematical subtraction um, algorithms, circuitry, and so forth, that we're stretching it and it won't ground balance anymore. Or it wants to throw the baby out with the bathwater and says, oh, well, that's a target. No, it's very close to ground. We'll throw that out as well. So that needs to be experimented with to find out if you can do it with these detectors. I'd say you can, but I haven't done it, so I can't be definitive and say, yes, you can. I'll say, maybe you can. So if anyone wants to do that, try it. Anyway, we'll get onto this here. What I found. Now this is interesting, right? That I'll turn that up. You can have a listen. This is this detector running flat stick, full bore, in normal mode, and I've got it the electronics trimmed for this particular coil, so it's very, very balanced. It's utilizing the cancel mode in the detector, which is all around that 4053 and a few little resistors there. And what was getting me is what I suspected was cross-channel coupling noise in that ADG 333, and it's such low level stuff. It's very, very hard to prove unless you amplify it up. So what I actually did to prove it, I did some tests, and rather than have this ADG 333 switching the input MOSFETs and whatever else it's switching, I think it switches part of the transmit circuit and damping. What I did is I've actually got my own driver circuit in here on that board. It's just a couple of transistors, and I've just hooked it up onto one of the rails here. There's a little voltage multiplier set up here, and yeah, I've tapped in on the output of the ADG 333, and I've also got rid of that BC whatever it was 857, I think it was, sitting in there. That's a gate discharge. The way it works, I'll probably have to explain it, but the transistor that sits in here, which goes to the gates, does not drive the gates. It actually removes current when the bias has been removed from the transistor. So it's to try and, well, actually, it turns off the transistors. Even though it's a slug of a circuit and a slug of a way of doing it, it still works. But I've driven it hard with a driven circuit here, and that turns it on and off really fast. And it's more snappy. There's a lot more current available. I love turning on MOSFETs hard. If it says the gate will take 20 volts on it, and I can supply an amp of current to something that's only rated for a a very small charge of 5 nanocoulombs or something like that. I'll say here you can have an amp and you have 20 volts as well. It's not going to do anything, but I like hitting those gates hard and make sure they're stable. I don't want any possibility of noise getting into the gate circuit. And that's what threw me onto doing some work on this thing here, because I had a look at the specs on it. It's got okay specs. It's slow. It's a slug. It's got about 300 nanosecond delay for on and off, and I think it's good for a few milliamps of current. And what else was there with it? Oh yeah, at 80 dB or so of crosstalk um, leakage. Right? Well, should I say separation? I won't call it leakage. Well, it sort of is. But what I've done, I've bypassed the critical um, drive to those MOSFETs on the input stage. So if there's any contamination here, it's not going to get in. So, and testing has indicated that I can hear stuff much um, much further out, harder to hear targets than how you would normally discern a small target. So I think it's a winner. So I need to do a little bit more experimentation on this thing here. I've added an extra capacitor, as you can see, just to smooth it out a little bit more and reduce the impedance. Those caps there, those ceramic-y, whatever they are, don't have a very low internal impedance. So Electro's nice low impedance cap within reason. So that's what I've done with this, and I've tried to speed it up and see how quick I can get it going. I've got it running away there. So yeah, doing that has been rather interesting, to say the least. It will work the same in enhance as it does in normal and sharp timings. The like what actually happens with this at the moment, I'll give you an idea. I've got this opened up. Say because I've got no limits on where I've set the frequency or the timing control. There's no limits. I can go off the chart. So I don't set up detectors. When I do it for other people, when I put the timing in there, I have it usually between 44 and 30 microseconds. I don't try and push the envelope because, you can get into a situation, right? This is quite funny, that if you actually had it, you could adjust the detector and say you hit 26 microseconds or something of dead time, and then the detector decided to go into coilover current. Well, how are you going to recover from it? Every time you turn it on, it's going to go into coilover current, and you're going to pull your hair out. You're going to have to pad the capacitance to get it out. Actually, you could probably just disconnect the coil and it would work. I haven't. Should I try that? Maybe I should. Okay, because I know at the moment, if I take this up, I'll just show you what happens, right? So this is. Well, I'll turn it down. You'll see on the screen anyway what happens when I go too far. It'll go out of lock in a minute or so. Well, no, it's probably already gone through that bit. Okay, you can see the timing coming right in. Look, it's gone completely unstable. Now I'll turn that down. Okay, and then I'll go a little bit more. There you go. And coilover current, she's turned off. So I have to actually turn that off. Now what I'll do, I'll disconnect the coil and I'll just see if it turns back on. I haven't done this. I don't know. So this is new to me. And we'll see what it does. Oh no. Okay, it actually works. So the reset mechanism has dropped the coil off. Before I was padding the capacitor to do it. So I've learned something. Put the coil back on, turn it back on, and it all fires up again. So yeah, that was a proving it had a failsafe there because obviously coil over current. Get rid of the coil. There can't be any coil over current anymore, can there? I think that's self-explanatory, and I wasn't thinking far enough ahead on that one. So that's that. And as I say, she's beautifully quiet. She's really, really quiet. Normally, with the oscilloscope running, these oscilloscopes will generate a little bit of power supply noise into these detectors, especially if you have a look at it there. I've got the I've got the leads and things directly connected to the gate to the MOSFETs, so that probably may inject a little bit of noise into the system, and still working quite well. So like I say, of all these detector things, there's plenty of experiments to do. I don't know how far you want to go. I remember we used to do on the GPs. We used to do the storage capacitors across the op amps, where you set them up to act as integrators and basically hold the charge from your signal and ground noises and so forth. Basically, how the ground balance works. But on this detector here, you could try. I'll get a pointy implement. You could actually try changing the values of these capacitors here. I think they're 18 nanofarad. If you that one, that one, that one, that one, and that one, I don't even know if you need to do the N one, but match them anyway. Match all these together. You can experiment. You could put in 32 nanofarads and see if you could double the filtering. It might just work exactly the same as turn the stabilizer up. But like I say, I haven't done it. There's so many things you can do with these detectors. There's tons of stuff you can do to it. You can go and do magnetic shielding on inductors. You can, do a whole heap of stuff. You even you could do those caps. You could probably even play around with these other bigger ones here. I think they're probably the same value. Where's that scrappy board I've got? It's probably getting more scrappy by the day, this board. But also, whoopsie, if you want to have a play, right, I've got to put on my eyeglasses to see where I'm going to poke here, right? But where these can't remember, they TLE 2022s or 2027s or something, TLC, which one's which. You see the resistors here, that one, and that one, and they're all the same on each. You could probably experiment changing resistor values. Actually, yep, there, and there. You can experiment changing the resistor values, which probably is adjusting the gain and part of the filtering in that area. And you could see, keep them all the same and measure them before you do it too. If you want to replace it with the correct values. You can play around with a lot of this stuff and, just make a note of what you did and what the effect was. You can have a look here that, at one stage in the design of these detectors, that's pretty obvious that, there was going to be possibly a trim pot here, and there's a trim pot position. Oh, that was all under the white paint, of course. So you got your channels coming in, 5 channels on these, 5 trim pots. Pretty logical. So I think actually, if you measure them, there's I think they're just basically hard connected. So I don't know what the story about that was or was intended to do. Maybe it was going to be some fine trimming or something. Maybe there's a device, a resistor in the circuit which is a 0 ohm, which may have been not going to be 0 ohm, and it was maybe it was 1,000 ohms, and there was a trim pot to fine trim the values. I'm only speculating here. I don't know. I didn't design this. The designer knows, but I don't think they're going to tell us. Um, so, I really haven't had a really hard look around here. I just know that, that footprint there is obviously for trim pots. That is what I am guessing. These capacitors here as well, they look like low loss type capacitors, not ceramic by the look of them. Let me have a good look. Well, they might be ceramic. Again, I've never fiddled with this stuff, There's only so many hours in a day. Imagine going doing all that, and I'd never get any work done. To the other side, do it again. Uh, you know, there's a lot you can do. There's heaps you can do. You could experiment on one of these detectors for the rest of your life. I absolutely convinced of that. So, even just doing what I've done on this one, just that there, well, you can make that board up and duplicate it. You could get rid of that ADG 333 and just work out the inputs. Just get a data sheet. It tells you what inputs go to what outputs, and just select the supply rails and drive it hard with a couple of dedicated devices. You're going to hit it harder with more current. I don't think you have to worry about the transmit, because I think that the transmitter on all these detectors anyway has its own totem pole drivers there. I think even on the flyback stabilization circuit, it's got a P&N channel, which basically that's not totem pole, that's current steerage, we call that, because it's using that MOSFET as a resistor. So it's a little bit one way, a little bit the other way. It's just a feedback loop, keeps it at a constant voltage. What else is there? There's some funny stuff in here. Um, I'll take off all that stuff there. But there's funny stuff like this device here. I think that's a 273 for memory, and all the inputs are all parallel up together, and all the outputs are all parallel up together, and that drives the MOSFET on the power supply. I thought that was one way of getting some good gate current in there. You just get a device like this and just parallel all the inputs and outputs, and then you're gonna get hit hard. Uh, yeah, things like that. I had a chuckle when I saw that, but hey, it works. Yeah. What else is there? Yes, a lot of other stuff. Um, but yeah. Anyway, if you want to get some lower noise out of these things on the receive, you could also also what I did here too. I actually have a 10 ohm resistor in series with the gate drive. Now you got to remember on these detectors too, every damn gate on this side and the other side of the board, right? Because it's NFETs everywhere, are all hard connected, right? There's no gate current sharing, or not that you really need it, but textbook. If you look at a textbook example, it'll all have 5 or 10 ohm or 20 ohm resistors on each gate leg. It's meant to stop oscillations. I'd never seen these things oscillate in a million years. They're hard. They switch hard. They don't do anything weird. But if you want to be pedantic, you can cut all the tracks, or you can stand up all the resistors off all the gate legs and wire them all up that way. Is there an improvement to be had? Don't know. Might be, might not be too. I don't know. So, like I say, you can experiment with this. You can just go completely bonkers with it if you want. That's why I love these, because they're easy to work on. If you make a mistake and blow it up, it's fairly easy to fix. Just don't blow up the processor. The rest of it's just pedestrian stuff. Um, all the components are easy to get, except for some funny little chip around near the processor. Um, yeah, I'm just thinking, is there anything really special? No, there's not actually. So, you know, you can have a really good play, and you know, you can improve it and just keep on improving it. A lot of things to do. Like you could probably make up a board, maybe 5 or 6 times as big as this. You could probably even use smaller componentry. I use this. I got these little boards. What it is, it changes SOT 23 to SOT 223, and there's a different footprint under the board. But I just used it for these and stuck them on, and easy. But you could design up a board and just stick it in here and wire it all onto the pins of that, and get rid of that if you wanted to, and dedicate it in separate componentry. And these things will supply these transistors here. You get 100 milliamps out of those easy. This thing here, I don't know what it puts out, 10, 20. Not that it really makes much difference, but just the way I do things in driving MOSFETs that are on any signal lines, I hit them hard as I can. I have a beautifully filtered supply rail, best I could do it. Um, you know, on here, maybe you should have, another sub supply, and you could use some series um, devices like they do on the power supply down here for the front end, and you could put some capacitance multiplier type circuits there, and then switch off that with a nice decent sized reservoir capacitor. Um, yeah, tons of stuff you can do. Anyway, that's enough waffle. It's probably given everybody enough food for thought to play around. But that has been an improvement. That is definitely an improvement over that. I think it's a crosstalk issue. I'm not 100% sure. Uh, you know, maybe it's laggy or something. I don't know. I haven't really gone into the degrees of it. I just looked at the. I was going to say schematic then. I just had a look at the circuit, right? And, yeah, just saw the way that was configured, and yeah, said, "Oh, that can be improved." And that's exactly what I did. So it didn't go into the nitty gritty analysing the existing topology of how it all worked too much. Didn't go there and nitpick it. And, oh yeah. I said, no, this can be done better, and will alleviate all these other possible problems that could possibly exist. Do I have to say in my opinion? Yeah, it's in my opinion. So that's that. So you can have a play around with these detectors, and yeah, if you find anything interesting, put in the comments, and I can tell everyone about it. Anyway, catch us later. That's good enough for this one.